Welcome, this is Professor Ridge, and today's lesson 3.2, Domain and Range. So our first learning objective will be find the domain of a function defined by an equation. Example 1, finding the domain of a function as a set of ordered pairs. Find the domain of the following function. So we got these 5 ordered pairs, 210, 310, 420, 530, and 640. So the domain is simply, if you recall from an earlier section, the domain is the set of all the input values, or the x values if you have ordered pairs. So 2, 3, 4, 5, and 6. And we're going to use this roster notation where we list out each member of the set, which in this case the set is the domain of the function. So we list 2, 3, 4, 5, 6. Now this didn't ask you to identify the range, but just to kind of review, the range is the set of the output values for each of these ordered pairs. So that'll be the 10, 10, and remember, when you do roster notation, you don't have to write the repeats. So 10 and 10, just write 110, and then the 20, 30, and 40. So that's the range. But again, the question just wanted the domain, so just the first part. Example 2, finding the domain of a function. So find the domain of the function f of x is equal to x squared minus 1. Okay, so up here we have the technique. Your first step, identify the input values. So again, the domain is the input values. A better question is you want to identify any restrictions on the input and exclude those values. So typically the things that we look for is if you have a function where you have like a fraction, right, a rational expression, and you want, if you have a 0 in the denominator, you want to restrict that. You're not allowed to have 0 in the denominator, because any number divided by 0 is undefined, and to be a function you have to have an output value. So this wouldn't give you a value. And then the other thing, we like real numbers too. So if you have a even root and you have a negative in here, this is an imaginary number. We want a real number output. So we have to restrict the domain, right? So you want to restrict that. So those are the two things that we kind of look for. So we're going to start with all real numbers and then look for any exclusions, right? And then we would like to write our domain in interval form. So you're going to think about the real number line. So if we have the real number line x axis, okay, and we start with negative infinity to infinity, and then look to see if there's any restrictions. So there's nothing here that's going to cause a problem. So the domain is going to be the real numbers, all real numbers. So it's going to be that whole x-axis. Example 3, finding the domain of a function involving a denominator. So find the domain of the function f of x is equal to x plus 1 over 2 minus x. So here's a rational function. And see, the book kind of fleshed out the number 2 here for your restrictions. So if there's a denominator in the function's formula, right, like this example 3, you're going to set the denominator equal to 0 and solve for x. And that's going to be the restriction. You're going to exclude that. If the function's formula contains an even root, set the radicand greater than or equal to 0, then solve. Right? And then write your domain in interval form. Make sure to exclude any restricted values from the domain. Okay, so for our exclusion here, we don't want this denominator to be equal to 0. So 2 minus x cannot equal 0. Okay, so up here they said set it equals 0 and solve, and then you're going to exclude that. You can, me personally, I just put a not equal sign here, like that, and then solve that, and that is my domain. We'll just do it the way it says up there. So I'm going to add x to both sides. So x is equal to 2 would make the bottom equal to 0, so I have to restrict. So I have to restrict this from the domain. So our domain is going to be everything but 2. So again, if we think of the number line, and we're going to go to 2, and we put an open circle there to say, hey, that's not part of the solution set, or not solution set, sorry, the domain. So that's excluded from the domain. Basically, you're going to get these two pieces. You're going to get negative infinity to 2. So again, interval notation, negative infinity to 2. We're not including 2, so it's a parenthesis. Right, so that's the left side. Now the right side's going to be, so you do union. So we're going to start at 2. We're not including 2, so it's a parenthesis. And then we're going to go on to infinity. So that would be our domain. Example 4, find the domain of a function with an even root. Find the domain of the function f of x is equal to square root of 7 minus x. So, you know, I find it's a little contradictory here. It says if a function's formula contains an even root, set the radicand greater than or equal to 0. See, the idea is, the restriction is the radicand can't be a negative. So if the restriction is it can't be negative, what it can be is it can be greater than or equal to 0. It can be positive or 0. So basically here, instead of saying, okay, what's the restriction and then exclude it, they're just saying, all right, what's the domain? Well, this number has to be a positive number to get a real number when you square root it. So 7 minus x has to be greater than or equal to 0, and then you solve that. So let's see, I can add x to both sides. Now remember, when you write using this inequality, when you want the solution set, you want to put the x on the left side. So when you switch it around, you got to switch the inequality sign as well. So the bigger number is the bigger number. 7's bigger than x. X is smaller, so it's less than or equal to 7. And again, if you think number line, for interval notation, we're going to start at negative infinity, and we're going to go up to 7. We're including the endpoint 7, so we put a bracket, right? And that's our domain. All right, let's review this using notation specify domain and range. So this is in the book, figure 5. I wrote graph in here. So here's the graph on the number line on the x-axis. Okay, so if you have an open circle at 5, we're saying we're going to not include 5. We're going to go up to 10. 10's included. So it's all the numbers in between 5 and 10. Not including 5, but including 10. So the inequality notation's written, as you see here, 5 is less than h is less than or equal to 10. Now when you do set builder notation, remember you're writing down, you're describing the conditions to be a member of the set. So you can't see that very well. That's a brace. So you got the brace, the set of all h's, such that 5 is less than h is less than or equal to 10. So it's just the same as the inequality. And then you have the closed brace. Let me try that again. Okay. Now for the interval notation, looking at the graph, you do from start, stop. So you're going to start at 5. You put a parenthesis. Now that's hard to see because we're not including 5. And we're going to do all the numbers between 5 and 10. You're stopping at 10, and you put a bracket. Okay. So it'd be from 5 to 10, like that. Okay, and you can see all the other ones. So this one, the 5's included, so you have the bracket on the 5. And the 10 is not included, so the parentheses there. Right? And then this one, both endpoints are not included, so they're both parentheses. And then this one is, it's all the numbers less than 10. So this goes off to negative infinity. and it stops at 10. And then one thing to remember is infinity, negative infinity, always has parentheses. And then we're stopping at 10, and it's not included, so it's a parenthesis. And then this one, 10 is included, so you got a bracket at the 10, and then it's going all the numbers greater than 10, so it's going off to infinity. Okay, and then if you have the whole number line that's all real numbers, this little fancy symbol here stands for the set of all real numbers, so it's just an R with an extra line in it. You can also write this using the set notation. You can say like the set of all x's, or in this case we've been using h. The set of all h's such that, and then you can write in words, h is a real number. And then close brace. Oh, that was pretty bad. There we go. Okay, and then the interval notation is just negative infinity to infinity with parentheses. All right, so that's a good little review. And again, that's in the book, Figure 5, if you want to look at it a little bit closer. Example 5, describing sets on the real number line. Describe the intervals of values shown in Figure 6 using inequality notation, set builder, and interval. So all three notations. All right, so inequality. So we have the numbers in between 1 and 3. We're including the endpoints. So we're going to do 1 is less than or equal to x. It's less than or equal to 3. And then we have this distinct, we have two distinct intervals. So we have this one, and then we can put U for union. And then we have the second piece is going to be, we can use union. The book writes the word or, so we can do or. So the second piece would be, we're starting at 5, and we're going greater than 5. We're not including 5, so it's just strictly greater than. Okay, so this is our inequality. Okay, now we're going to do the set builder. So basically it's exactly this, except you're going to put the braces, the set of all x's, such that, and then just write that inequality down exactly the way we did it here. You can use or union. And then our interval notation would be, you're going to do the first piece, start, stop. We're including the endpoints, so we're going to use the brackets. 1, 3. So again, this describes all the numbers between 1 and 3, including the endpoints. And then union. Technically, you can write or as well, but usually in interval notation, we use the union symbol, which means or. And then this interval, again, we're starting at 5 and we're going on forever. So that would be from 5 with a parenthesis, because we're not including 5. Go on to infinity. And again, infinity always use parentheses. I know you heard me say that about 5 or 6 times, so you'll hear me say it a bunch. Finding domain and range from graphs. So this skill, a lot of students have trouble at first when they first see it. But you got to remember, we're taking this graph. Remember, graph is just well, there's a lot of things we can say about a graph. It's a picture of the solution set for an equation. It's also, right, it's all these points on this graph, and each of these points make up x and y. So this is an infinite number of ordered pairs that we can see this picture of. So for instance, this point right here is the point -5, 5. So if we were saying, hey, what's the domain, we're going to get all the x values. So -5, what's the x value of this point? Well, it's -4.9, right? So the domain is going to start at this point here, and it's going to contain all the x coordinates for all these points. So the domain's going to be from this point here, x is -5, and it's going to and it's going with the arrowhead. It's just going to go on forever to infinity. So our domain's going to be, so you think of the x coordinates. So it's from -5, and it's going forever. So it'll be from -5 to infinity. And then a range, well, let's see. It's here's the top. Now, when you do the range, right, you're going to go from the bottom up if you do it in interval notation. So our range is from -infinity, and it stops here at 5. So range is the y values. So if this is the top, and then the bottom, it goes forever. So the range is from -infinity up to 5. -infinity to 5 included. Okay, so find the domain and range from a graph. Find the domain and range of the function f, whose graph is shown in figure 9. So a couple ways I can think of this. So if the graph is continuous, right, there's no gaps or anything, you could draw it without picking up your pencil. One method to do is I could do what I call my box method. If I can draw a rectangle, here, let's do it like this. Let's make this kind of, if I can draw a rectangle that's going to contain the highest and the lowest point, right, the domain's going to be on the x-axis, so from this spot to this spot, right, this is the domain, and then the range is going to be the y value. So starting from, actually it's right here down to here, so that'll be my range. Okay, so let me erase all that so we can look at it again. Okay, so our domain, now notice this one, it's open circle, so it doesn't hit 0, but this looks like it hits 0. It's hard to tell on there, but it looks like it hits 0 there. So the domain is going to be, well, not the domain, the range is going to be from -4 to 0, right? So the range is, let's see, it actually hits here because of this one, even though that one's open. And it's all the points in between, all the way down to 4. So that's going to be, or we'll do that one in red. So that's going to be my range. And again, my domain, we'll do that one in this purplish color. It's going to start here at 3, but it's an open circle. And it's going to stop at 1, and that's a closed circle. Okay, so my domain is equal to, well, we're going from -3 to 1, and we're going to have an open circle, so a parenthesis for -3 to 1. So all the numbers in between those. 1 is included, so that's going to be a bracket. And then our range goes from -4 up to 0. -4 up to 0. We're looking at the y values, right? So this is 0. This is -4 on the y values. So it's from negative, remember you do from the smallest to the largest. So -4 to 0. And then they're both included, so brackets. -4 to 0. Example 7, finding the domain and range from a graph of oil production. So here's figure 11. Domain and range. So we want the lowest to the highest on the y-axis for your range. So you can see the lowest value. Make this one for range red. Here's the lowest value. And here's the highest value. So it's just above 2,000. And then it hits every point in between that, right? So the range is going to be from just under 200. So I don't know if we want to estimate that. They tell us anything anywhere else? So we're just going to roughly estimate that. The book looks like they're estimating that to be about 180. And then for the domain, we're starting here at whatever the starting year is. So it's not 0, it's like 174, 173, 1973. And then it's going all the way to the end of, that's about 2010, I guess. If you measure this distance, it looks about 2010. Okay, so the domain would be, remember it's the x-axis, so 1973, and we're going to include the 1973 to 2010, and then the range, we're going to estimate that about 180, and then that is, I don't know, 2000, was the book calling that 2008? Where they got that, I don't know. Okay, so that's the range. Sometimes when you have graphs that are interactive, you can click on it and it'll tell you what that point is. All right. Finding domains and ranges of the toolkit functions. So in an earlier section, we went over a bunch of functions that you should know, the graph of them, quickly, and these come up a lot, the basic functions. So we can identify the domain and range of those that we did earlier. So the constant function, remember, it would be y equals some number. So if y equals 5, you go to 5 on the y-axis and draw a horizontal line. So the domain is going to be all real numbers. See, the domain again is the x-axis. So it's negative infinity to infinity. And the range is just the single number c. And the way you write that in interval notation, you're starting at c, including it. You're ending at c, and include it. You can also write it using roster notation, just with the braces. But in interval notation, that's the way you write it. Okay? Begins and ends with c. This was our identity function. So y equals f of x, or f of x equals x. Okay, y equals x, I meant. Y equals x, or f of x equals x. So the input and the output are the same. So 0, 0, 1, 1, 2, 2, so on. And the domain is going to be all real numbers, and the range is going to be all real numbers. All right, our next function is the absolute value function. Y equals absolute value of x. So you get the v, right? 0, 0, 1, 1, 2, 2. Absolute value negative 1 is 1. Absolute value negative 2 is 2. You get this v. And the domain's all real numbers. But now look at the range. If you think about the y values, it starts at 0 and it goes up to infinity. So it's 0 to infinity. All right, and then a quadratic function, or we said a square function. The graph's a parabola, and the domain is all real numbers, and the range is from 0 to infinity, just like the absolute value one. Okay, so those are the same, domain and range, even though they look different. They have the same domain and range. All right, our next function is the cubic function. F of x is equal to x cubed. So again, we get this nice cubic curve. 0, 0, 1, 1, 2, 8. Right, so I'm just thinking of the table that we did earlier. Anyway, so you got the cubic function, and you can see if you look at the domain, it's going to be all real numbers, and the range is also going to be all real numbers. Okay, and then the reciprocal function. So here we got a fraction. The bottom can't be 0. So see, that restricts the domain, and you can look at the graph. It's never going to hit the y-axis, right? There's no value on that one. So x can't be 0, again, because of the fraction. So the domain's from negative infinity to 0. So if you think about this, the domain is negative infinity to 0 with parentheses, and then from 0 to infinity. And the range, same thing, right? It's from negative infinity to 0, and then 0 to infinity. So the same domain and range. Okay, can't be 0 for x, can't be 0 for y. Okay, so our next one is the reciprocal square function, 1 over x squared. So again, just like the reciprocal one, the bottom can't be 0. So the domain is negative infinity to 0. Again, your domain, you're looking at the x-axis, right? Can't be equal to 0. So it's negative infinity to 0, and then 0 to infinity. Okay. Now the range, if you the other way that I think of this, if I were to think of this as like a trash compactor, and I move these to smoosh into the y-axis, we're going to get basically all these points. That will be my range. So this point gets smashed right there. This point will get smashed right there. So on. Smash, smash. So we're going to get all the points get smashed onto the y-axis, and the domain would be from 0 to infinity, not including 0. Okay. The next function is square root function. This is a solid dot here, so if I think of that trash compactor method, that's the way I describe it in class usually, right? If I can take these plates and smoosh them onto the x-axis, this point would get smooshed right there, this point would get smooshed right there, so on. You can get all these. Basically, you're going to get just the positive x-axis where the splat would be, is what I call it, right? So it would be from 0 to infinity, and we're including 0. Now if I turn my trash compactor this way and I smash it onto the y-axis, sorry, domain's y, this point will get smashed right there, this point will get smashed right there, so on, right? And you can see you get all these points. So it'll be from 0 to infinity. Okay, and let me erase that so you can see it. Erase that one so you can see it. Okay, so the domain's from 0 to infinity, and the range is from 0 to infinity. So domain's the x-axis, range is the y-axis. And then our last toolkit function is the cube root function, f of x equals cube root of x. And again, if we do this, if we think domain's the x-axis, and again, if I kind of smash all the points onto the x-axis with my plates here, this point would get smashed up to here, so on. You could see that you're going to get all real numbers. These would get smashed down here. This one. So I'm basically pushing this point down till I hit the x-axis. Down till I hit the x-axis. So you're going to get all real numbers, right? And then the same thing now if I turn my trash compactor plate sideways. Oops, 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 oops. Sideways. This point would get smashed there. This point would get smashed there. And this is going forever. It's still going down real slowly, right? But it's going down forever. So your domain's going to, your range, sorry, we're doing the y-axis, is going to be from negative infinity to infinity as well. So all real numbers. So given the formula for a function, determine the domain and range. Exclude from the domain any input values that result in division by 0. Exclude from the domain any input values that have non-real or undefined number outputs. So anything that's not real or you get undefined, you got to exclude it. Use the valid input values to determine the range of the output values. Look at the function graph and table values to confirm actual function behavior. So if we use our toolkit functions, find the domain and range. So if you recall that x to the third is going to be, let's go back and look. X to the third, our cube function. Where'd it go? There it is, cube function. It's going to be all real numbers. And then we're going to subtract from that x. So that would be like the identity function. So that would have the domain. There's a little more to this, but basically just if you add or subtract polynomial kind of things, your domain and range are going to be basically, you're just going to exclude any. You can think of these individually. If I can exclude something from this one, I'll exclude from this difference, right? So nothing's getting excluded from x cubed, nothing's getting excluded from x. Everything's going to be fine. So our domain is going to be negative infinity to negative infinity. And then if you think about the range, this is pretty much going to overpower the x. You're still going to get basically this kind of shape with some minor differences going on in the middle here, but overall you're going to get that basic shape, and the range is going to still be negative infinity to infinity. We'll talk more about this later, but for now, don't worry about it too much. All right, finding the domain and range. So find the domain and range of f of x equals 2 over x plus 1. So again, we're going to exclude from the domain any input values that results in division by 0. So anything that makes that bottom, the denominator, equal to 0, you're going to exclude it. So what makes that equal to 0, and you're going to exclude it? So you subtract 1. So x, we're going to exclude it. So x can't be negative 1. So your domain is going to be negative infinity to negative 1 union negative 1 to infinity. Now, basically, this is going to have the same shape as the reciprocal function. The 2 is going to do some things to it again. We're going to talk about what all these numbers actually do to the graph. But if you think about the output values, you're going to do 2 divided by some number, and basically you're going to get something similar to this graph. Where was the 1 over x? So if you have 2 over x plus 1, we'll learn about some of these, what we call transformations. But basically the overall shape is going to be similar to this. It's just going to get shifted, and then the 2 is going to kind of distort the shape a little bit. But the basic shape is going to be something similar to this. And so your output values are actually going to be the same from negative infinity to 0. And we'll learn again about that in more detail later. So don't worry about it too much. You can graph this on Desmos if you're not sure, and look at the domain and range there. So the domain is everything except negative 1, and then the range is all real numbers except 0. There's no way to get 2 divided by a number and get 0. Everything else will happen. Example 10, find the domain and range of the function f of x is equal to 2 times square root of x plus 4. So remember, a square root function has this basic shape like that. So if we think about our toolkit function, right, the basic one, the domain's from 0 to infinity and the range is from 0 to infinity. But we have this x plus 4 here. It's not just square root of x, and we have this times 2. We're going to learn in a later section, what the actual effect that is to the graph. So don't worry about it too much right now. Just go back to our idea that the radicand has to be, for the domain, the number under the square root, if it's an even root, has to be greater than or equal to 0. So we solve that. So x is greater than or equal to -4. So our domain's going to be -4 to infinity. And so basically, instead of starting at 0, we're going to be at -4, and we're going to have this basic shape. The 2 is going to do something to the shape a little bit. It's actually, I'll kind of let the cat out of the bag here. It's going to give it a vertical stretch, so it's going to make it like something like that by a factor of 2. So it's going to have that still basic square root shape, but a little distorted because of the 2, and the -4 shifts it left 4. And again, we're going to learn about that in a later section or chapter. So don't stress about it yet. You'll learn about it. You can always go to Desmos, type this in here, and look at it if you're not sure. So the range, or you can just kind of reason. Look, okay, so if I put in numbers, I'm going to add 4, take the square root of it. That'll give me a positive number times 2, right? And then the bigger this x is, the bigger this overall value is going to be, and it'll just go on to infinity. So it's going to be from, so if you put in -4, you get 0. Square root of 0 is 0, times 2 is 0. So we're going to start at 0, and then again it's going to go off to infinity. So the bigger the x value is, the bigger the y value will be, right? And one more time, you can, if you know about the graph, you can kind of think about the graph. If you don't know what the graph is, go to Desmos, type it in there, see what it looks like, and you can determine it that way. So you got a lot of options to figure out the answer for these. Okay, and now we're going to do our last learning objective, graph piecewise defined functions. Graphing piecewise defined functions. A piecewise function is a function in which more than one formula is used to define the output values. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. We notate this idea like this. So we have the name of the function. F is a function of x, right? So f of x is equal to, and then you're going to have the 3 formulas. You're going to use formula 1 if x is in domain for formula 1. You can use formula 2 if x is in the domain for formula 2. And then you're going to use formula 3 if x is in the domain for formula 3. So look, here's an example of a piecewise defined function. Absolute value function, you can define it this way. There's 2 cases, right? If x is greater than or equal to 0, well, think about what kind of numbers are greater than or equal to 0. So here's 0. Greater than or equal to 0 would be all these numbers. So like if x is 0, you're going to use this one. So the absolute value of 0 says you're going to just leave it alone. The absolute value of x is just x if x is 0 or more. So if it's 5, absolute x is greater than 5, so that's in here, and this says you just leave x alone. So if x is 5, the absolute value of 5 is just x, which is 5. Now on this one, don't read this as negative x. Think of this as the opposite of x. So the absolute value of x is the opposite of x if x is less than 0. So think about on the number line, what kind of numbers are less than 0? Well, those are negative numbers. So if I had did absolute value of -3, -3 is over here, which is less than 0. So I'm going to use this function. So the absolute value of -3 is the opposite of -3, which we know is just 3. Okay? So that's how you write it in piecewise notation for absolute value. All right, how to. Given a piecewise function, write a formula and identify the domain for each interval. So 1, you identify the intervals for which different rules apply. 2, you're going to determine formulas to describe how to calculate an output from an input in each of the intervals. Use braces and if statements to write the function. Okay, so example 11, writing a piecewise function. A museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for a group of 10 or more people. Write a function relating the number of people in to the cost C. Okay, so we want to write the costs as a function of n using, so we're going to have two cases. So first let's identify the, so if n is from 1 to 9 people, so let's see, if n is, we're going to use a inequality like this, right? It's going to be $5 per person. So how would you make the function to be $5 per person? We're going to say cost is $5 per number per person. So it'll be like that, 5n. So the way we do this here is we're going to write 5, basically we're going to write this on the top line. So 5n if, sometimes you put a comma here, if 0, oh, here's what the book did. They didn't use the equal to. They went from 0 to n to 10. Same thing. Okay, I'm going to write it the way the book did it. 0 to n to 10. So if it's less than 10 people, it's $5 per person. Okay, so groups of 1 to 9. Kind of like the way I did it. It's more the way that they wrote it here. But anyway, this is the way the book's listing it. And you can see you get it's the same result. Okay, so now you get a fixed cost. It's just a flat fee of $50 if the group is 10 or more people. So for that one, if the group is 10 or more people, so if n is greater than or equal to 10 or more, then the cost is equal to a flat rate of $50. So we put 50 if n is greater than or equal to 10, right? And that's the piecewise defined function. Okay, and the book shows a graph for that function. So if you were to graph it, so look at from 0 to 10, this, basically if you did y equals 5n, it would be the 0 would be 0. And if you did 9 people, that would be $45. So they drew this line. Technically, right, it shouldn't be a continuous thing because you can't have like 0.2 people. But anyway, that's the way the book did it. And then it's just a flat $50 for anything bigger than 10. Okay, so they converted this to a continuous function. Again, it probably shouldn't be, but that's okay. It's just to kind of illustrate the idea. And also, if I were to try to get the function from the graph, see right here I can see where it's two different function formulas, right? So I can kind of like say, all right, here's where it's splitting. Actually, let me change this to here. it's kind of splitting right here at 10. So if it's less than 10, you're going to use this function, which is the 5n. And if it's greater than 10, you're going to use just the constant function 50. It's going to be flat. Example 12, working with a piecewise function. A cell phone company uses the function below to determine the cost in dollars for G gigabytes of data transfer. So cost is a function of G, so C of G is equal to 25 if you use between 0 and 2 gigabytes of data. And then it's $25, the flat fee, plus $10 times G minus 2 if G is greater than or equal to 2. Okay, so if it's bigger than 2, you got to do the $25 plus 10 times whatever G minus 2 is. Find the cost of using 1.5 gigabytes of data. So they're asking you to find, so for the first part here, find, we want to rewrite this, C of 1.5. So first you got to decide, okay, is G equal to 1.5, is it in this one, so question mark, or is it in this one? Is G is 1.5 between 0 and 2, or is it bigger than 2? Well, obviously it's this one, so I'm going to use just 25. Okay? All right, let me erase that. Now, let's do part B. What about 4 gigabytes? So what's C of 4? So again, your first step is say, okay, if G is equal to 4, am I using the top function or the bottom, the top piece of the function or the bottom piece of the function? So 4 is greater than 2, so that's going to be the bottom one. So I'm going to do 25 plus 10, 4 minus 2. So you plug in the 4 for the G. 4 minus 2 is 2. So that's $20 plus 45. 25 is 45. So it's $45. Okay, so how to, given a piecewise function, sketch a graph. So indicate on the x-axis the boundaries defined by the intervals of each piece of the domain. For each piece of the domain, graph on that interval using corresponding equation pertaining to that piece. Do not graph two functions over one interval because it would violate criteria of function, meaning you can only have one y value for every x value. So you can't get 3 different answers. You can only get one answer. Okay? So the first step is I always look at this portion right here. Right? That's how I'm going to split my x-axis. So if you think of it this way, we're going to be x is less than 1, and then to 2. So basically, if this is at 1 and this is 2, so this portion of the graph over here is x is less than or equal to 1. This middle portion of the graph is x is between, between 1 and 2. And then this portion of the graph is x is greater than 2. So on this portion, the left portion of the graph, we're going to do the top one, x squared. So if you think about your x squared function, kind of looks like a parabola. Well, not kind of, it is a parabola. But we're going to go to x is 1, which is right here, and we're going to erase that portion of the graph. Basically from there. Oh, that didn't work very well. Like that. So that's going to be on this portion of the graph. right, let me start over here. All right, I want to do this a little nicer. So I made the graph here. So parabola is 0, 0, 1, 1, and then I'm going to stop at this point. So normally I would do 2, 4, 3, 9. Well, it's up there. And then the parabola will come around. See, negative 1, 1, negative 2, 4, negative 3, 9, which is up here. So my parabola, now this one, oh yeah, it does have a solid dot because of the equal to. So basically you're going to have this parabola. Oh, let's see if I can do this. Oops, I missed it. Okay. Pretend I hit it close enough. Okay, so that's the top portion. Now y is equal to 3. Well, y equals 3 is just a horizontal line, but I'm just going to draw it through this portion, and it's going to be an open circle here and a closed circle there because of it's just strictly a less than, and that's strict less than or equal to. So that'd be a solid dot. And remember, y equals 3 is just a horizontal line. And then x. So if I were to graph that line, y equals x, that's your identity function. So it'd be like negative 3, it'd be this thing. Right? Negative 3, negative 3, negative 2, negative 2, negative 1, negative 1, 0, 0, 1, 1, 2, 2, 3, 3, so on. But again, we're just doing it for the bottom portion that's greater than 0. So we're not going to do that whole thing. We're going to start here where that red line is. And I'm going to put an open circle on that one. I guess I should have made this black. Okay, so that'll be the piecewise defined function. Look just like that. The graph of it. Okay, and then that brings us to the end of the section. Make sure you practice, practice, practice. So do as many of the exercises you can and submit them to Canvas. All right, talk to you next time.